I just want to start by saying how grateful everyone here at Thayer and I and all the overseers are that you're all here together to celebrate what's an amazing event, 150 years of Thayer School of Engineering. Yeah, big deal, right? So someone here wrote some just amazing words about why we're here, and I really want to, if it's okay, just take a minute to read them because I think they're really beautiful. So why are we here? We are here to highlight the innovative and entrepreneurial endeavors of our faculty and alumni and share their stories of impact, exploring how engineering education can assist in solving some of the world's most complex problems in business, industry, the environment, and human life. We are here to bring alumni back to campus to showcase Thayer's commitment to innovation and engineering education and to celebrate Thayer's 150th anniversary. We are here to provide meaningful social and educational engagement opportunities while strengthening our alumni community. And we are here to educate alumni on Thayer's achievements and the impact our liberal arts engineers have had on the world. So we have an amazing program for you this morning. I know you know that already, but we're going to start, and these are icons, in my view, just amazing. So we start with Professor Eric Fossum, and it's going to take me a while to get through this, but I can go as fast as I can. So buckle up. Dr. Eric Fossum is a professor at the Thayer School of Engineering at Dartmouth, director of the school's PhD Innovation Program, and associate provost for entrepreneurship and technology transfer at Dartmouth. He is a semiconductor device physicist, an engineer specializing in image sensor technology, and is currently exploring, brace yourself, the quanta image sensor. He is best known for the invention of the CMOS image sensor, now used in billions of cameras, and has been called by many, including Joe Helby last night, who stole my line. I guess you said Katie Couric actually was the first one to say it. The father of the selfie. Thank you, Eric. He was inducted into the U.S. National Inventors Hall of Fame in 2011 and is a member of the National Academy of Engineering and a charter fellow of the National Academy of Inventors. Get this, in 2017, it was announced that he would receive the Queen Elizabeth Prize for Engineering, the highest global prize in engineering. He received his BS in Physics and Engineering from Trinity College in Connecticut, his PhD from Yale University in 1984, and became a double E faculty member at Columbia University. In 1990, he was recruited to the NASA Jet Propulsion Laboratory at Caltech, where he managed JPL's image sensor and focal plane technology R&D and invented the CMOS image sensor. He then co-founded and led Photobit Corporation, and I'm running out of breath here, to commercialize the technology. Photobit was acquired by Micron in 2001. He later served as CEO of Simpel Corporation to commercialize MEMS autofocus actuators for camera phones. He worked with Samsung Electronics before joining Dartmouth in 2010. He has published over 290 technical papers and has over 160 U.S. patents. Dr. Fossum co-founded the International Image Sensor Society, IISS, and served as its first president. Now, just to try to humanize these guys a little bit, the last line says, he and his wife operate a hobby farm in New Hampshire, and he enjoys his time on his tractor, hopefully not taking too many selfies while he's doing it. Dr. Eric Fossum.
Well, good morning. Can you hear me? Okay, great. So it's a great honor to be the warm-up band this morning. It's really, and I'm serious, dead serious. It is really a great honor. And continuing that musical band analogy, I just want to say that, I think most bands, older bands, when they're on a road, the fans all want to hear the old stuff, and the band wants to play the new stuff. So I've divided my show into two halves: the old stuff and then the new stuff. So anyway, without further ado, let me just get started here. So I think this is one of my favorite photographers, Ansel Adams, and he is shown here on his with his mobile camera, taking pictures of Yosemite. And if you go to Yosemite today, probably you'll be shooting with a different kind of camera, which is the cell phone camera, which, of course, there are now about 4 billion cameras made every year, and most of those are in smartphones. So with all those cameras out there, what do people do? Well, they take pictures. So I found this data a few weeks ago. This is uploaded pictures per day in billions. You see it looks a lot like an exponential curve. So being a good engineer, I decided that I would plot this on a log plot, semi-log plot, and in fact, it's actually a remarkably straight line here. And if you extrapolate, that's about 6 to 10 billion photos uploaded every day to the internet, which is kind of staggering. And it's increasing about 2x per year. So in 2020, maybe we're up to about 100 billion photos uploaded per day. I mean, is that sustainable? I don't know. It's just, we live in a very narcissistic society or something. All right, so we are we're in a school here, so just a couple of things. So most of you probably know this, but light is both considered electromagnetic wave, and it's also considered as a particle. So these particles of light come, and each one carries a certain amount of energy, which we perceive as color. And then we see basically the sum of all these integrated over time. So light goes into a camera. I took this picture, by the way, with my cell phone. But anyway, it goes in a camera, and actually the camera's kind of interesting because the light goes to the lens, and there we use the electromagnetic wave property of light to bend the light and to focus the light. And then it strikes the semiconductor chip, the image sensor. That's my business. And there it's the quantum nature of light that we care about. And the photons strike the image sensor. Took amazing pictures. In fact, it's just now coming to the end of its life. It's been deorbited and will burn up in Saturn's atmosphere soon. Sad to say. But this particular camera, which you can see is quite large, weighs about 60 kilos, burns 30 watts, and delivers a megapixel snapshot, which wasn't bad at the time. But when Dan Golden came into NASA around that same time, his idea was, hey, these giant spacecraft are really killing NASA budget-wise and time-wise and everything else, so we need to do things that are faster and better and cheaper. And for my particular job at JPL, that meant we had to miniaturize these cameras to reduce the mass, power, and cost. So, okay, so we need to invent something that can allow this big CCD camera to be shrunk. And I think most of you know that if we integrate electronics on the same chip, we can make things smaller, and that's been the power of the electronics industry for some time. Unfortunately, the recipe you need to make the charge-coupled device is quite different than the recipe for making mainstream CMOS microelectronics. So you could conceivably do them at the same time, but it's kind of like baking a pie cake at the same time. And it's possible, but it's not practical. So actually we needed a new invention to make it possible. So my invention is this active pixel, blah, 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 blah. And well, now we just call it CMOS image sensor, by the way. But anyway, the light comes into a particular pixel. We divide an image, of course, even in the CCD, into lots of pixels. These are my 3 daughters, by the way. They all went into science. But anyway, the light comes in. We generate electrons. And then inside every pixel, we have an amplifier. And the trick here is to reset the amplifier first. And then we transfer the electrons to the capacitor, where they're converted to a voltage. For those of you that remember electrical engineering, it's kind of a basic relationship. And then we read out that voltage. And the only, not the only trick, but the key trick here, in fact, the key trick here is that we make the measurement before we transfer the electrons, and we make it again after we transfer the electrons, and we just look at the change in voltage. That's kind of like going to the deli counter, and when you buy something, you want them to weigh the container first, and then they put the food in it and weigh it again, right, and take the difference. So that's why you get a true measurement of what you're buying. So same thing here. So once you do that, you can build this camera on a chip where you have the pixels like you had in the CCD, except they're different pixels. But you can also integrate now all the analog electronics. You can integrate A to D converters and all digital electronics all on the same chip and make large cameras into very tiny cameras. So this was, for example, a module that we were building at my second company, Simpel, where actually not only did we have the camera on a chip inside, but we also had a MEMS device to move the lens for autofocus. Unfortunately, that technology did not overcome the incumbent technology, which is voice coils. So if you look at your camera phone today, it doesn't have this in it, sad to say, even though it was better. So it was an interesting lesson. So anyway, you find that in your camera phone. So anyway, I didn't do this myself. I had a team at JPL. You can tell this was a few years ago from our fashionable eyewear. And then, we looked at this and said, this technology is really good here on Earth. I tried to convince U.S. companies to commercialize this technology. They're all like, that's interesting. Thank you very much. Maybe next year. So I got frustrated, and we decided to start our own company. Sabrina Kemeny, Nick Dudamopoulos, Bob Nixon, and myself, which we called Photobit. You can see the photons coming in and the bits coming out in our logo. I can tell you it was a big uphill battle. The CCD guys did not want to let the newcomer in, and I could talk for a long time about that process. But anyway, after what I call the perspiration phase, which lasted about 6 years, we grew to about 135 people. We did not take any venture financing. We did strategic business investment along with SBR programs. I also mentioned that not only you may have a couple of patents that you start a company with, but in the end you wind up developing a lot more patents as you actually have to bring that technology from a prototype into a commercializable product. And so we were in this Intel web camera, these just as examples, the dental X-ray sensors, the swallow pill camera, and just around 2000 or 2001, this was taking off. And one of the reasons why we decided to sell the company is we realized in order to really compete in that market, which was going to be gigantic, as I've already pointed out, we just couldn't grow fast enough from 135 people to capture that market. As I like to say, it's like trying to catch a whale from a rowboat. It's just like really hard to do. So anyway, we sold the company, which actually wasn't so bad, all in all. This is the company at around 2000 or so. So today, what's happened since then, it's got a life of its own. The semiconductor sales last year were about 10 billion. That's the semiconductor, not the whole camera. There's been thousands of engineers working around the globe on this technology, so it's really improved quite a bit over the years. And the other thing that happened is that after we sold the company, the patents went back to Caltech, and then they successfully enforced their patents against all the major players. And won everything. And I keep hoping they'll name a building after me at Caltech. But They should. It's there. It's well, I'm working on that, Joe. I'm working on it. But it's the highest. I believe it's the highest royalty revenue stream at Caltech. So anyway, as Joe mentioned, this was the glory phase. This is the glory phase. So not only myself, but George Smith, who invented the CCD, Willard Boyle, who also invented it, has passed away. Mike Thompson did the first CCD image sensor. Nobu Teranishi, who did the first device back in the 80s, a special photodiode device, and then myself. So this shows Mike holding my phone, trying to take a picture of us. He didn't actually know how to use this. But it made a great picture. I actually had to take the picture. So that's down here. And this is Her Royal Highness Princess Anne, who we got to meet. And we'll go back and be able to, at the pleasure of Buckingham Palace, we will get the actual award from the Queen. Anyway, now that's the old music, right? I got a few minutes for the new music. What I'm doing here at Dartmouth actually started from an idea I had in 2005, which is that if we could count every single photon, actually I go back here, if we can count every single photon as it comes into the sensor, that would be a different kind of way to do imaging. So conceptually, we get this binary data from whether a photon hit a pixel or did not hit a pixel. We have lots of these, maybe 1 billion. We then create these kind of binary images, but we take a lot of them per second, so maybe 1,000 per second. And then we combine the data not only in X and Y, but also in time, so we get this little cubicle thing. And by analyzing this data, we create one grayscale image pixel, which has all kinds of interesting characteristics, which I don't have time to go into right now, but that's the concept. Unfortunately, I was running the MEMS company at the time that I had this idea, so it just kind of sat around for a while. I filed a patent, but it sat around for a while. When I came to Dartmouth, it was one of the goals that I had was to try to implement this thing. Joe was very patient when I explained to him what my lofty goals were. But anyway, I wanted to build this little tiny photodetector. We want pixel sizes that are less than 1 micron, and 1 micron is very small, by the way. I wanted to read this large array of maybe 1 billion pixels out, so a gigapixel at high speed, like 1,000 times per second. So that's something on the order of a terabit per second of data on this chip, which is also a big number. And by the way, we have to do the electronics so they don't melt down. So basically less than a watt on the chip. So this is like a great university research project. Okay, years and years of things to work on. So we set out to sail with my group here, and actually I can tell you that there's no way this would have happened without these great graduate students that worked with me. They did a lot of the heavy lifting on this, got to work with them closely, still working with them. It's been a wonderful experience for me, I have to say. It's all about me. So they delivered too. This is just this year. We built, this is a 2nd generation chip. It's got about 100 million transistors on it. It was designed just by 3 people, 3 of my graduate students. I didn't actually think it was going to work, to be honest with you. It was just like too much to do in too little time. But it does work. It works great. This looks a lot like a technical slide. It is. But this is what you need to know. This is the output signal from 1 pixel, and you see that sometimes the signal is here, and sometimes here, and here, and here, etc. If we turn up the light a little higher, we get a little broader distribution, and more light, and more light. And the key thing here is that each one of these peaks corresponds to exactly an increase of 1 electron in the signal. Electrons are quantized, and this output signal that comes off of that capacitor, really tiny capacitor, that voltage is also quantized, and that's why we have these discrete peaks. The other interesting thing is that the ratio of the heights of these peaks exactly matches Poisson distribution for light when it comes in. So that's why we know it's really working. Amazing. We built a camera, took a picture of a leopard printed on a piece of paper. This is the data blown up and back away a little bit. And this is what it looks like. Take a lot of frames, and then we can generate a very nice grayscale image from this prototype sensor. So it's actually working. So anyway, lots of interesting applications. So this is very good for very low light sensing. That's probably the key attribute, the new tool that we didn't have before. Now we can really count photons in very large arrays one at a time. It's very important for astronomy, neuroscience, microscopy, other biological life science things. Also very interesting for computational imaging, and also very important for national defense. Turns out it's also a great quantum random number generator for encryption. So anyway, so just on the tails of that success, we spun off yet another company, which will be called is called GigaJot, that my two PhD students will operate, and we'll see what happens. So that's the story to date. Thank you. Chris tells me there's time for a couple of questions, if there are any questions, which I'm happy to answer. Yes, please.
So what's happened to the charts a couple of days?
Well, the very first paper I wrote was active pixel sensors are CCD's dinosaurs, and everybody laughed at that. But as it's kind of turned out, over 20 years, CCDs have been pushed back into just one or two remaining niche applications, which really are more about just legacy than anything else. So they're still around. Actually, astronomers still like to use them. For them, the CMOS image sensor is not compelling enough to switch over. So I understand that. It's okay. But are those 4 billion cameras, maybe a few 100,000 are CCD cameras. Yes?
What are you using to amplify the photon?
Right, so the photon goes in and generates an electron, and then we convert that electron to a voltage using a really tiny capacitor. So one of the key technologies here is how to build a really, really small capacitor so we get a voltage out that is more than just the background thermal noise. So that's really where the amplification takes place, is just through that capacitance.
So you don't amplify the electron and have it like bounce around and then spout out more electrons and then
Okay, actually you're describing something called an avalanche process, where you put a high electric field on the electron and it slams into the crystal and generates more electrons, et cetera. So that can be used for detection, but then you get very large arrays, very large pixels that are also very difficult to manufacture with high yield. So it's possible, but it won't be suitable for this application. Yes?
In that picture, are those trench capacitors you're using in that image?
No, they're not. It's a floating diffusion capacitor. It's like a p-n junction, actually. Okay. Oh, wait, one more. Yes?
Do you extend your quantum image sensor to color images as well, or right now are you using it black and white?
Yes, definitely can do color. So we just haven't gotten there yet, but that's very straightforward, I think. Yes?
Two brand new PhD graduates running this company?
So, well, you know, yes. So it's like, it reminds me when I taught my daughters how to drive in Los Angeles. Okay, so they are very smart, capable. I will still have a hand in providing some advice and things to them, but at least at this stage of the company, they are the right people to lead it. Yeah. Okay, thanks.